Hi, my name is Wayne Francis. I'm the engineering lead for the AutoDive Mussel platform that you see behind me here. What I'd like to do is walk you through some of the design features and some of the activity that we've put forward in building this system. This platform is intended to be a 20 by 20 support structure for the ropes that the mussels adhere to as they grow. This platform will support up to 40-foot long ropes, and we expect that they would be on a grid along the 20 by 20 wood structure. What you'll see here is we have a displacement tank which will contain a water-air mix. The compressed air pushes water out through the exit pipes, which are located here at the end, and then intakes will be suspended into the water on this side. Those intakes will bring water in. The top vessels, of which there are two, are dry wells. They contain our batteries, our electronics, our communications gear for the platform itself. Those electronics are specifically designed to be able to maintain the system along with the compressed air stored in the side tanks for a period of 3 months, servicing the weight growth of the mussels themselves, as well as the weight growth associated with fouling. Now we're in our facility interior. I'm standing next to our 15-foot depth cistern. 15 feet of depth, a 4-foot roughly diameter radius. That allows us to put this structure, which is our scale model, in and adjust the buoyancy to take us to various depths up to 15 feet of depth. That's more than plenty of room for us to understand the mechanics of the control loop, as well as the various components that we've put into the system. I want to walk you through our scale model now. You can see we have a pressure vessel here, which allows us to store the electronics and valve assemblies. Then we have a displacement tank, similar to the large tanks on the Mussel platform, and a compressed air tank here. These hoses are the same types of hoses, same diameters, same structural consistency as the hoses that we use on the full-scale platform, and that allows us to evaluate flow rates through the valves, flow rates through the hoses. So we understand not just how air is moving, but how much quantity of air we can move in a given time frame. This electronics assembly allows us to test the individual components to make tweaks to our control loop respecting the various capabilities of the electronics. It also allows us to evaluate the control of the various tiers of systems. For us to control the air through the system, we use air-controlled valves, which are in turn controlled by electrically controlled valves. So you have pneumatic valves here and electronic valves here, as well as the electronics that house the control loop, communications to the control system, the user control station, as well as the key sensors, including temperature and pressure measurement at various key points in the system, including the storage tanks and the ambient water depth. Those controls allow us to manage the buoyancy of this system by displacing water with air or allowing water to push air out, changing the overall density of the system, moving it up and down in the water column. This is our on-site test pool, which we use as a wet lab when we're evaluating the electronics on the fully assembled system. This allows us to pre-test before disassembling and deploying the system. This is a fairly shallow pool, but it gives us enough depth for us to reach an intermediate depth and then bottom out and then bring it back up. It allows us to do a complete end-to-end test of these systems, again, before disassembly and preparation for cartage to the end user site.